let's continue on with our KSPs here. Well, we have solubility in water. That's our standard KSP, but we can alter the solubility by adding a common ion, and in fact, just decrease the solubility by adding a common ion. So, this is precipitation. Precipitation, there are a couple of things we'll see. When we calculate Q, which is the reaction quotient that we covered back in chapter 15, compare it to KSP. If QSP is greater than KSP, then we are going to get precipitation. QSP is equal to KSP, then we call it a saturated solution. And then if QSP is less than KSP, then it's an unsaturated solution. Nothing should happen. And so when we're looking at our previous example of silver chloride solid, and this is going to silver ion plus chloride ion. Here, if we increase any of these ions, then we're going to decrease the solubility. So the common ion effect is we're going to start off with some initial ion here, would be silver ion or chloride or both, and then figure out what's going to happen with the solubility. Yeah. And so we'll use this to calculate our QSP. It's going to be the initial concentrations there. All right, so the basic problems that deal with this, or just, you take, let's say, 50 milliliters of 0.100 molar silver ion, and then add a drop of chloride, and then see what happens. Will we get a precipitate or not? And so if we start off with 50.0 milliliters of 0.100 molar silver ions, this silver ions could be from something like silver nitrate. And then we add 1 drop of HCl. And this will be 6.0 molar. Will we get a precipitate here? And so, a particular question like this, we wouldn't be calculating first the solubility in pure water. What we do is we just look at what we have here. And so this is going to be just like chapter 17, in which we have to do a solution dilution, or a initial step here. And so if I have 50.0, a drop of water is about 0.05 milliliters. So we'll just say 50.05 milliliters would be the final volume for this. And then calculate the new concentrations. For HCl, we're going to get a dilution of 0.05 to 50.05. So it's going to be significantly diluted, the 6.0 molar. We aren't allowed that many sig figs, but we'll just carry some extras. And so what does this come out to? Can somebody punch this out?
Okay. Okay, 0.0599.
0.0599?
Yeah.
All right.
Well,
0.005?
wait, how come?
0.00599.
Just repunch it and calculate it.
I did.
John.
All right, and then we go on to the silver ion. The silver ion, or the silver nitrate, both are the same. It's 1-to-1. The same thing with this. This is the same as concentration of chloride. And this is going to be a 50 to 50.05 dilution of 0.100 molar. So what does that give us here? It's barely diluted.
0.09990.
3 nines and a
Yes,
0? Okay. Something like that. All right. Looks right. All right, then what we do is we calculate QSP. And then compare it to KSP. This one, it's pretty obvious. Does it look like it's going to precipitate?
It was less than.
Because if we look at KSP, KSP is 1.8 times 10 to the minus 10. It's a very small number. And so it does look like it's going to precipitate. Right? And so if we calculate our QSP value, we just take these initials, right, and multiply those out. And so let's just see what QSP is. So if we calculate QSP, QSP is the initial silver ion times the initial chloride ion concentration. So what does that come out to?
5.988 times 10 to the negative 4.
Times 10 to the negative 4, which is much greater than KSP, therefore precipitation. And so one of the questions we might get asked is, yeah, well, we have too many ions in solution here. It's not going to last. So we'll get a precipitated curve. All right, the next question might be, well, what percent of the silver ion will precipitate with just 1 drop of 6 molar HCl? Okay, so let's answer that question next. Do I get a significant percentage, just 1 drop, or just a minimal? And so how would I start this particular problem? Well, you know, in all our problems with the KSP, we always write the equation the same way. Solid goes to the ions like this. Whether it's precipitation or dissolution or solubility or whatever, it's always written backwards or forward in the case of dissolution, but we just leave it like this. We could write it backwards, but you know, it's not worth doing because the KSP values, you know, we'd have to invert it. And either way, yeah, so it's just best to just get used to working like this. And so we have 2 choices though for this particular problem because what we know is we have too many ions in solution, so it's going to precipitate 0.0999 is too much initial silver, 0.00599 too much chloride. And so what we could say is we could just do this. We could do minus X molar, where X is the moles per liter that precipitate out of solution. So this would be the precipitation. But the problem is a lot of these are highly insoluble, and so the amount of precipitation is close to 100%. When the amount of precipitation is close to 100%, then your calculator might have trouble because it might just round it to 100%. Right? And therefore, in this particular chapter, we usually reset. In fact, we always reset to the side that's favored. In this case, the left side is favored. For KFs, you know, which we'll see later today, KFs, the right side's favored. And so for KSPs, we usually reset to the left. For KFs, we reset to the right. Just to make life easier, because if your calculator ends up rounding, then we don't have to redo the problem. Here. And so here, I wouldn't set it up like this. I'd just go ahead and, you know, this is a really small K, so that means the forward reaction isn't all that favored, but the reverse is highly favored. And so we just reset it to the right. So let's reset this. Just rewrite it here. Silver plus with chloride. All right, then if we reset this to the left, that means we're going to precipitate out all the what? Silver ion or all the chloride ion, or both?
Right.
All the chloride, because that's the limiting reagent. Because the chloride's going to go to 0 molar, but that's going to leave some excess silver ion left over. And how much am I going to have left over?
Subtraction.
Yeah, just a subtraction there. Point.
We got 0.094 left over.
0.094.
Yeah, 0.040.
So this is what we call common ion. The common ion type problem is where, since there's already a lot of silver here, the solubility is actually going to be less than the solubility would be in pure water. And when we think about it, okay, we precipitated out all the chloride, but that's not equilibrium, because if we calculate Q here, Q would be 0, which means it's got to shift to the right. And therefore, we're going to have to dissolve some of that. So when we dissolve this, now this is the solubility, because this is what the maximum amount of silver chloride that can dissolve is in this common ion, or in the presence of this common ion. And so we ended up with 0.0940 plus S. Now, here, there's a big difference in the setup. The big thing is X is going to be big here, because, in the reverse direction, it's 10 to the positive 10, roughly. And so X is big. Simplifying assumption will definitely fail. But over here, S should be small, therefore the simplifying assumption should work, making your life a little bit easier as far as the math goes. Especially since a lot of these, will have coefficients here that aren't 1, and this particular one's pretty easy because the coefficients are 1 and it's second order. It's not that bad. And so we'll just plug in the concentrations here, 0.0940 plus S times S. And then the simplifying assumption should work, no problem, 940 times S. And that gives us an S equal to that's equal to 1.8 times 10 minus 10. Yeah.
Well, mine I don't think has enough digits, but it's 0.0, 1 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9.
Do you have more?
But it's zeroed out my calculator, so I'm saying that might not be enough digits.
All right.
I have 1.91.
1.91
Yeah.
molar. Then we double check it, right? Was the simplifying assumption valid? Yeah, 10 to the minus 9, 10 minus 2, no impact there. So this is just going to be 0.0940, pretty much molar. And then the S here, 1.91 times 10 to the minus 9 molar. And so in this case, the concentration of the chloride is equal to the concentration of silver chloride that dissolves, which is equal to the solubility. The concentration of silver ion is not equal to solubility because we had a whole bunch from a different source to begin with, probably the silver nitrate, right? And so that's it. We double check this to make sure, it'd be 10 to the minus. Yeah, that looks about right. 2 times 9 is 1.8. So this double checks okay. Now, how are we going to figure out the percent precipitation? Over here, the one great advantage of this is percent precipitation is easy because it's just X over your initial. So if we wanted the percent precipitation of silver ion, just be X divided by your initial. This is how much precipitated times 100. But over here, it's a bit more convoluted. How are we going to figure out the percent precipitation over here? What are the steps involved in figuring out the percent precipitation? Because this silver ion here, 0.0940 molar, is what we call the,
Excess reagent.
no, not the excess. It is the excess reagent, but we don't call it the excess reagent. We call this concentration right here we call this concentration the silver ion remaining unprecipitated. And so what
Why?
because that's the silver ion concentration you're going to have in solution that doesn't precipitate. This is the equilibrium silver ion concentration. And so what we do is we calculate the percent silver remaining in solution. And so that's going to equal 0.0940 divided by the original amount. Yeah, the original amount is 0.0999, right? That was the initial silver that we had before we reset it. And then this is to be times 100%. And so what was the percent of the silver? 94.09. 94.09%. Was that, does this qualify as a complete precipitation?
No.
No, about maybe one more drop of HCl and it would have been
Complete.
complete. Complete as far as, well, as far as what, this totally arbitrary cutoff. The arbitrary cutoff is 99.9. Some people need more than 99.9% precipitation, right? Well, this way of controlling solubility can be put to use. By controlling the solubilities by using common ion. Common ion in this case could be just precipitating agent, you know, or whatever. Common ions maybe too general of a term, but let's talk about.
Excuse me, is hydroxide a good precipitating agent?
Yes, hydroxide is an excellent precipitating agent because it precipitates everything except for group 1, calcium, strontium, barium, ammonium.
Professor, if that's the amount that was unprecipitated, the original question was what's the percent that will precipitate, so you just take it away from 100?
Oh, yeah. Actually, I was wrong then. This is not the amount that precipitated. This is the amount that didn't precipitate, which means we have to do one more calculation.
100 minus that.
Yeah, we have to get 100% minus this. And so the percent silver ion that actually precipitated is equal to
6.01 or something.
Yeah.
5.01, sorry.
5.91. Oh, we didn't precipitate much. We didn't precipitate much. This is a more convoluted way of doing it, but it's worth it because the reset will save you a lot of work, you know. And so we only precipitated out about 6%. And so we're gonna need a lot more drops of silver chloride to do it.
HCl.
You know, one question might be how many drops, right? How many drops would it take you to precipitate it out?
Will each drop provide the same amount of precipitate per se?
No.
Right?
No, because each drop results in solution dilution.
Change in the double.
Right, and so, you know, how would you solve this problem? Well, this would be a very similar, you know, problem as we did earlier. You know, if you look back at our titration calculations, we had two types of calculations. You know, I don't know if you summarize these yourself, but one type of calculation is you're given the start, you figure out the end. The end is pH. The other type of calculation, you're given the end and you figure out the start, right? And so this one would be, if I asked you, you know, how many drops it would require to get 99.9%, I'm giving you the end, you have to figure out the start. And so the setup is the same as what we're doing for the titration. In fact, you want to do that problem?
Sure.
All right, so how many drops of 6.0 molar HCl would be needed for 99.9% precipitation? So this would be a challenging problem, right? I think. So let's see how we might solve it. All right. So what we have is we have 50.0 milliliters of 0.100 molar silver ions. And to this, we're going to add the 6.0 molar HCl, and or chloride. And we're going to do plus Z milliliters, and then we'll just convert milliliters into drops. That'd be easier than having two different units here. Right, plus Z milliliters. And so what we're going to have is, we're going to have at the end of this, we're going to have 50.0 plus Z, right? And then we do our solution dilution, correct? Solution dilution would be the HCl is going to be a Z over 50 plus Z dilution of 6.0 molar, and the silver ions would be 50.0 over 50.0 plus Z 0.100 molar. Then we just set up our ice table. Got the silver chloride solid goes to silver ions plus chloride ions initial. Then we plug in our initial here. Our initials here would be like this. This would be the initial silver, and this would be the initial chloride. The initial chloride is the same, of course, as initial HCl. The 1-to-1 mole ratio. Here, you know, I guess we could reset it, but if we reset it, it's going to become more and more, convoluted. And so probably let's try it without resetting it, because if I reset it, then I would, it's just probably easier. We could try to reset it, but let's just try not to reset it right now and see what happens. All right, so what do I know? I know I need to precipitate out how much of this? 99.9%. So 99.9% would be 0.99 of our initial has to be precipitated out. So we got to lose that from our initial silver ion concentration. This is going to give me, is that 99? 9%. Yeah. And this is going to give me 0.001 of my initial silver ion concentration remaining unprecipitated. Right? And so here, this is easy because if I don't reset it, then this is just percent precipitation. Right? And then I'm going to lose the same amount over here, 0.999 of my silver initial. And so over here, this is going to be the chloride initial minus 0.999 of my silver initial. Okay, then I have to I'll plug this into my KSP equation. This is going to be the silver at equilibrium times the chloride equilibrium. So this is gonna be, let's add it in here. That times this, just plug this in. That in there. And then we, what do we do? We solve this for Z, to be in terms of one unknown, right, after substituting. All right, so this is kind of the reason why I do the problems the same way, except for the shortcuts, which really save time for the buffer. But in this chapter, there are a variety of different, you know, in the last chapter when we were doing titrations, they're all kind of the same, but in this chapter we have more places where we can go wrong, you know, where we can get mixed up. All right, this is one application for that. Solve for Z and then convert that into drops. I'll let you finish that, but this is the basic setup. Another example is something called fractional precipitation. Okay, so let's take a look at fractional. Fractional precipitation is where we have a mix of two ions. So let's say I have let's see, I forgot my book today, but you want to borrow mine? Maybe you can tell me what's the KSP for silver bromide?
Mr. Sandberg, KSP is given in appendix 3.
And chapter 18.
Oh,
The QSP, we got a 5, right? So concentrate on silver and concentrate on
Actually, maybe I should bring these up. Because the smaller the KSP, the lower the solubility in general, but it doesn't always work because of how the solid splits apart.
5.0 times 10 to the negative 13.
5.0 times 10 to the negative 13. Okay, if we compare the KSPs, you know, the KSP for silver chloride is 1.8 times 10 to the minus 10. And so if you look at the solubility product, it's a lot smaller for silver bromide. And so automatically you'd say silver bromide is less soluble than silver chloride, right? But solubility, that's just solubility in pure water, right? Solubility in pure water. But if we have common ion changes the solubility. And so we have to be very careful in which, you know, in how we interpret things. And not only that, if it splits up in different ways. For example, if we look at something like PbBr2, do you still have that table open, John? Yeah, PbBr2, is it there, lead 2 bromide?
No, but it might be in the back. Lead bromide, KSP 4.0 times 10 to the negative 5.
4.0 times 10 to the negative 5.
And so that's a lead 2 bromide, I don't know if there's a lead.
We also have to be careful because of how it splits up, because this will split up into 3 ions, this splits up into 2 ions. When it splits up into 3 ions, then solubility is a little bit more complicated. And so we can't.
Why would something split up into 3 ions?
Oh, it's made up of 3 ions. If it's made up of 3 ions, it's going to split up into 3 ions. If it's made up of 2 ions, it'll split up into 2 ions. And that's all we assume.
Let's
We
say
assume that's
calcium
ideal.
phosphate. calcium phosphate.
Splits
Oh,
up
that's
in-
gonna split up.
into 5 ions. Calcium phosphate will split up into 5 ions.
Uh-oh.
It splits up into 5 ions, then the solubility. One of the things that, I don't know, we did this, I think, calcium phosphate yesterday. Did we do that? Or we didn't do this? This should split up into 3 calciums. We're assuming ideal behavior.
3 minus on the phosphate.
Yeah, thanks. 3 minus. This splits up into 5 ions. So initially, if we say nothing's dissolved, then at equilibrium, this is going to be plus 3s plus 2s, where s is solubility of calcium phosphate. So for every calcium phosphate, we're going to get 3 times as much calcium and 2 times as much phosphate for every calcium phosphate that dissolves. So this is going to be 3s, this is going to be 2s. And so KSP is going to be the calcium ion concentration squared, or cubed, sorry, and times the phosphate ion concentration squared. And so this is going to be 3s cubed, 2s squared, which is going to give us 108s to the 5th. That means the solubility is equal to the KSP divided by 108 to the 1/5 power. And so we have to be careful because the solubility is tricky, because over here, this is just equal to s squared, right? And solubility is just the square root of the KSP. So solubility can be tricky to predict just based on the KSP. So what we normally do is we just calculate it and see what the solubility is. But you know, this is a calculation for pure water. There's no common ion here. If we add common ion, what happens to solubility? It changes, it goes down, solubility goes down. And so that further complicates things, you know, when we're looking at solubilities. And so if I had fractional precipitation like this, and I put in, I'm gonna put in 0.0500 molar chloride, and then I'll put in 250 molar bromide. Then which one precipitates first?
Which one precipitates first?
Yeah.
Bromide.
Bromide precipitates first because if you look at this, yeah, bromide, it's got a smaller KSP, can't sustain as many ions, it should precipitate first. And so we expect bromide to precipitate first. But if I had 0.250 molar chloride and 0.0500 molar bromide, which one precipitates first?
Chloride. The higher concentration.
Well, it's a higher concentration, so you expect it to precipitate first, but bromide's less soluble in general. And so we don't know which
Either
one
way.
precipitates first. So there's a question here about which one precipitates first. This one, it's easy because bromide's in higher concentration, plus it's got a solubility that's lower in pure water.
But what at this time, bromide?
So this one's more complex. And so what we're going to do is we're going to look at a fractional precipitation problem with this and see if we could separate it.
Interesting.
I'm going to make the if I made the concentrations the same, then it'd be easy. If it were let's say if it were 0.250 molar chloride and 0.250 molar bromide, which one precipitates first? Bromide would precipitate first. The same common ion effect, the lower solubility in general, so it should work. But I don't know in this scenario here which one's going to precipitate first. So let's do this. Let's take a look at this. If I had a solution that was that contained chloride and bromide, let's say I put some sodium chloride in here, some sodium bromide, and they happen to be different concentrations. I had a lot of chloride in there, 0.250 molar, but not much bromide, 0.0500 molar. bromide. All right. Can I separate this using silver ions? That is, I know they have different solubilities, so I'm going to slowly add silver ions. Slow addition.
Yeah, you should have the silver.
Why
Oh,
snow?
I'm sorry, it's CO. I don't know why I thought.
Because
Yeah, AgCl will precipitate.
the first question is, which one precipitates first? Do they precipitate at the same time? No, they don't precipitate at the same time.
No?
No. They don't precipitate at the same time because they have different solubilities. And what we're doing is, right now, why slow addition? Why slow addition is so I can start unsaturated.
Ah.
If I start unsaturated, that means, QSP is less than KSP. I'm good. And then what I want to do is I want to just slowly add the silver until I saturate one of them. When I saturate one of them, then saturate one of them, then the QSP is equal to the KSP. Right? So which one is going to become saturated first? Is it the bromide or is it the chloride?
Bromide.
And so, let's figure it out. Let's show it. And so what we need to do is we need to do a calculation here. We're going to calculate the silver ion concentration required to saturate the, first we'll do silver chloride. So the silver ion concentration required to saturate for silver chloride. And so the silver ion concentration times the chloride ion concentration, when it's saturated, is going to equal 1.8 times 10 to the minus 10. And therefore, the silver ion concentration required to saturate is going to be 1.8 times 10 to the minus 10, depending on how much chloride we have. The more chloride we have, the less silver we need. The less chloride we have, the more silver we need. And so, well, we know how much chloride we have, 0.250 molar. So this is going to be 1.8 times 10 to the minus 10 divided by 0.250, which is going to give us what? Concentration.
7.20 times 10 to the negative 10.
7.20 times 10 to the negative 10?
Yeah.
Okay. Then we repeat this calculation for silver bromide. For silver bromide, we want to saturate it, so the silver ion concentration times the bromide ion concentration has got to equal 1.8 times 10 to the minus 10. It can't be less than this. It should be greater than this. Greater.
Why though?
If it's greater, we call it supersaturated, which means it's going to precipitate out. It's got to be equal. Mm-hmm.
That's a different KSP.
Oh. Yeah. It can't be 1. It's got to be 5.0 times 10 to the negative 13. Thanks.
Okay.
And so the silver ion concentration is going to be 5.0 times 10 to the minus 13 divided by how much bromide we have. We only have 0.0500 bromide. Which means that, what's the molarity of silver that's required? That's 10 minus 2. 1 times 10, 1.0 times 10 to the minus 11 mole. So, if my calculation is correct there, then that means bromide will precipitate out first, right? But what if I made bromide 0.00500?
Uh-oh.
If I made bromide 0.00500, then chloride would have precipitated first. Chloride would have precipitated first because this would be down by an order of magnitude, which means this requires less. And so what we see is that which one requires less silver? This one. All right. So we take that and we increase the silver ion concentration. When the silver ion concentration equals 1.0 times 10 to the minus 11, then this is what we have in the solution. We have silver ions at 1.0 times 10 to the minus 11 molar. We have chloride ions at 0.250? Yeah, 0.250 molar. And we have bromide ions at 0.0500 molar, right? And then we calculate our Qs. When we calculate our Qs, calculate QSP here. Well, this is going to be 1 times 10 to the minus 11. This is going to be 2.5 times 10 to the minus 12. 2.5 times 10 to the minus 12.
How do you get that out?
I just multiply them. Well, 2.5 times 10 to the minus 12, QSP is smaller than KSP. QSP is smaller than KSP, which means that silver and chloride are what we call unsaturated. Unsaturated. Okay, then we compare this to silver and bromide. When we multiply these out, this comes out to QSP is equal to 5.0 times 10 to the minus 13, which is equal to KSP, which means it's saturated. And so the silver and the chloride are unsaturated, but the silver and the bromide are saturated. Okay, which means if I try to increase the silver some more, then the silver bromide is going to become supersaturated, which means it'll have to. In other words, QSP is greater than KSP, which means it's going to precipitate. And so what we'll do is we'll continue to increase the silver. When I continue to increase the silver bromide precipitates. Does all of it precipitate? No, just a little bit at a time precipitates, right?
Yes.
We can't get all of it to precipitate. So silver bromide, but I want all of it to precipitate. And so if I wanted all of it to precipitate, how much silver would I have to add? If I want all the bromide to precipitate? An infinite amount, right? I'm not going to be able to do that. And so I'm just going to keep adding until what? We want to maximize this. Because, you know, ideally what I'd like to do is I'd like to precipitate all the bromide and leave the chloride there. That gives us a way to separate chloride and bromide, both insoluble. And so we want to maximize this by adding more silver. But I have a problem. I can't add an infinite amount of silver, that's one. And two, if I keep adding silver, eventually what's going to happen? The Cl is going to precipitate, and both bromide and chloride will precipitate, and then I've got a mixture. But I just want something separate. And so maximize by adding silver until we want to stop. Stop when the silver ion concentration reaches a Raiston.
Yes.
How much silver ion was required to saturate silver chloride?
Chloride, 1.8 times 10 to the negative 4.
The silver ion concentration.
Oh, sorry.
What's that? 7.2 times 10 to the negative 10? Is that it? All right, thanks. If we go beyond this, then silver chloride will precipitate. And so what we want to do is we want to stop when the silver hits this, and then we've saturated, you know, with the solution with respect to silver chloride. If we continue, then both precipitate. Both ions precipitate. We don't want that. All right, so when we stop it here, that means the silver chloride won't precipitate because it's just saturated. We have to go beyond saturation to get precipitation. So the question is how much of the bromide did we precipitate at this point? How much bromide precipitated at this point? And so we need to calculate how much of the bromide we got out of solution. So how can we do that? Well, the way we do that is this. We do calculation. And the calculation is we calculate the percent bromide remaining in solution. Okay, the way we do that is we figure out at this silver ion concentration, which is 7.2 times 10 to the minus 10 molar, what is the bromide concentration? And so the bromide concentration is going to equal KSP divided by the silver ion concentration. Now we have a different silver ion concentration. We have much higher silver ion concentration. So we have a much higher silver ion concentration. The amount of bromide we have is going to be smaller. And so this is going to be the KSP divided by this, 7.2 times 10 to the minus 10, which gives us a bromide concentration of
6.94 times 10 to the negative 4.
times 10 to the negative 4. Oh, thanks. All right, so that's the bromide that remains at this point. This is the bromide that remains in solution. And so the percent bromide remaining is going to be this. Unprecipitated. Is equal to 6.94 times 10 to the minus 4 divided by our original. What was the original bromide? 0.250.
Oh, I'm sorry. It's
Oh no, 0.0500
Yeah, sorry.
times 100%. Which means what? Can someone calculate it? 0.0138. All right, percent. All right, therefore, the percent bromide precipitated
Oh, wait.
Yeah.
Forgot
You
to-
gotta multiply by 100 versus
Sorry.
it's 1.3.
1.38.
Yeah.
Okay, the percent precipitated is going to be 98.72. Is that right?
That's still not complete precipitation.
That's pretty close, but not complete.
Maybe 2 more drops?
No, if we did 2 more drops, what would happen?
Both are precipitated.
Both are precipitated. What is it?
95.62.
Oh, 95.62?
Or 98.62.
Ah.
Oh, yeah, 98. Yeah, you're right. 62 thing. 98.62%. All right, to be a good fractional precipitation or good separation, we need 99.9% precipitation. And so this one fails. I mean, it's close, but it fails. That's a good, so we don't have a clean. Although the silver bromide will be clean, the remaining solution we would call contaminated. Okay. If I started off with, well, that's it. All right, so fractional precipitation. Well, basically what we're doing is we're decreasing the solubility by adding common ion. In this case, the common ion is silver ion, and precipitating things out. We can also increase the solubility or decrease the solubility using pH. And so increasing or decreasing solubility using pH is KSPA. A stands for acid. So basically just add acid to it and see what happens, or base. Acid or base, so pH related. Some things will show significant dependence on pH, others don't. So for example, silver chloride, this really doesn't show much dependence on pH.
How about silver carbonate?
Silver carbonate would show a huge dependence on pH. So silver chloride, chloride's neutral. Silver ions are acidic, but it's not very significant.
How about iron?
Iron would show more significant dependence on pH. So let's look at silver carbonate and write that one up. Silver carbonate shows a significant pH dependence. And that's because carbonate is a base, a weak base. And so this is KSPA. KSPA is you take the KSP equation like this, and then you add acid. You add acid, well, acid's going to be hydronium plus. And then you look, what will the acid attack? Will the acid attack silver ions? No. Well, the acid is going to attack carbonate. And so the acid will attack carbonate. And then you go ahead and write out the equation. We're going to form bicarbonate and water. But what is the K for this? Equation.
We don't know.
We do know.
8.
We do know because reverse this equation and what does it look like?
Looks like formation of acid.
It looks like the Ka equation for bicarbonate. In fact, it is. And so this is 1 over the Ka. It's just the reverse of the Ka equation for bicarbonate. Well, the Ka for bicarbonate we can get off the table. You know, that table says 5.6 times 10 minus 11, but yours might be different. You have it?
I think it's 4.7 times 10 to the negative
4.7 times 10 to the negative 11?
11.
Okay. And it's going to be 1 over that, right? So we got to flip it over. And so what does it come out to?
2.127 times 10 to the negative 10.
Oh, wait, it's got to be positive.
Or it's 10 to the 10, sorry.
Yeah, 10 to the
Yes, I'm so used to saying the negative.
Okay. All right, what we have is multiple equilibria, right? When we do multiple equilibria, we usually start with the biggest K and then work down. But in this particular multiple equilibria, we cannot start with the biggest K. Why can't we start with this as our step 1? Why can't we just go ahead? Oh, this is the biggest K because KSP of silver carbonate. Actually, I just found the book. I don't want to make you do all the work.
Mostly leads to the chapter anyway.
Wait, what happens if we combine iron and carbonate? That is one of the
We
next.
got 8.5 times 10 to the negative 12.
Yes.
8.5 times 10 to the negative 12. And so in all the previous chapters, what we've always done is we started off with the biggest K and then work our way down, right? Because the smaller K's become less and less significant. But in this particular chapter, we cannot work with the biggest K because there's something
Why though?
missing. You know, I got multiple equilibria here because I know that the acid will attack the carbonate. So if I'm adjusting the pH, that's going to adjust the hydronium level, right?
Mm-hmm.
And so I got multiple equilibria because the pH will alter the carbonate level. Lots of hydronium, not much carbonate. Right?
Wait, what if we switch silver carbonate to iron carbonate? What will happen?
Same thing. Same thing. Exact same thing.
This is the carbonate.
We could do it high carbonate as well, but
Because iron is more acidic.
yeah, iron complicates things. If you do it, iron 3 carbonate, but essentially the same stuff. So what do we do here? Well, we start off with the biggest K, which would be the second, but we can't. Why? We don't have any carbonate. Where does the carbonate come from? The carbonate comes from the silver, the KSP. So we always got to start with the KSP in order to generate the ions so that they can be attacked by H+. And so it's impossible to start with the second step. Now, multiple equilibria, right? How do we solve multiple equilibria? We got to solve it simultaneously, or we do it stepwise. But the problem is do you think the second step is going to have a significant impact on the first step? Oh yeah, yeah. The second step is going to screw up the equilibrium in the first step for sure, right? Which means we have to do it simultaneously. But in this chapter, we have one more simplification that we can do. One more trick that we can do. And the trick involves this. If the first step, K, is very small, and the second step, K, is very big, then we can use the third method. The main method is simultaneous, and then we have stepwise, right? There's a third way we can do this. The third way is combined. I told you we can't do combined earlier, right? We couldn't do combined because of why? Because we're going to miss species, but in this particular scenario, we don't really miss any species. And so what we do is we combine the two equations. And combined works here because, well, let's see the problem with combined. Do you guys know the problem with combined? The problem with combined is my final equilibrium is missing species. What species is missing?
Carbonate, the two minus.
It's missing carbonate. It's missing carbonate. Right, so I'm missing a major species. But think about this. Does step 1 generate much carbonate? No, because K is very small. Does step 2 consume a lot of carbonate? Yes, because K is very big. And so I would expect a negligible amount of carbonate to actually exist. So
But
negligible, we're going to ignore it completely and say the carbonate is, and so most of the carbon is going to end up as bicarbonate here, not carbonate, right? And so then the combined works. The combined method works when we have a scenario like this, and then what we can do is to get the K for the combined equation, we just state the K, this is called KSP8, is equal to the KSP divided by Ka for bicarbonate. It's, in other words, we just multiply the two Ks. When we add up the equations, we multiply the Ks. Whereas it didn't work before, because before we couldn't use the combined like in phosphoric acid. You know, if we use the combined in phosphoric acid, then we'd say all the phosphorus ends up as phosphate. Well, that's not the case because most of it ends up as phosphoric acid and dihydrogen phosphate, right? Whereas if we combined it, it would end up as phosphoric acid and phosphate.
But how about monohydrogen phosphate?
Monohydrogen phosphate is, right, we'd be missing that too if we did the combined. And so in this chapter, combined can work, and that's KSPA right here. And so what we want to do is we can figure out this. Now we have a trick in doing this. You know, for example, this. What is the solubility of silver carbonate in a pH, let's make it a little bit acidic, pH 3.00 solution? Well, the trick in this chapter is we have two kind of levels here of difficulty. Actually, it's not hugely difficult. This is ambiguous. A little bit. It's ambiguous because is this pH the initial
Or final?
or both?
Both what? Both initial and final?
Both initial and final.
So the pH doesn't change?
Yeah. How can the pH not change? How can the pH not change even if you consume some acid?
Buffer.
Buffer, right. And so if this were a buffer solution, then it's easy because the pH at the initial is the same as the pH at the final, and any loss or gain is buffered. The final makes it easy too. And so if it's buffered, this is final. If it's initial, then it's a little bit harder. A little bit harder. These two are easier. This is a little harder. Because there's going to be a pH change that's going to happen. Let's see. Let's say if that were the initial pH, well, you know, this is a pure solid, so pure solids we just ignore. This is a pure liquid, so pure liquids we'll just ignore. And so we have the hydronium here, and if this were the initial pH, then it's a pH of 3.00, so it's 1.0 times 10 to the minus 3 molar initial hydronium here. And then we assume that nothing's dissolved, so this is going to be 0 and 0, right? And then there's going to be a change. The change here is going to be minus S plus 2S plus S. And so equilibrium, we're going to have 1.0 times 10 to the minus 3 minus S, 2S, and S. Actually, this is not that hard, is it? Maybe not.
Why do we use S?
Why would you use S? Because for every mole of silver carbonate that dissolves, we'll get 2 moles of silver. And so the relationship between S and the original silver carbonate and silver is we've got twice as many silver ions. Two silver ions break off for every silver carbonate. And then there's a 1-to-1 ratio here. And so it's just the mole ratios here. This works out. And so we can use S in place of X as long as we're starting off with zeros and letting it dissolve.
So we're trying to calculate how much dissolve?
Yeah. This is the solubility. The solubility is the maximum amount that will dissolve. And so what is the solubility of this at pH?
Oh,
3.
so that's why you use that. Okay, I get it.
Right, and what we're going to see is that the lower the pH, the higher the hydronium, the greater the solubility is going to be. And so the next step is just to calculate it out. And so this is going to equal 2, well, actually, let's write it since we got to get in the habit of writing the silver ion squared times the bicarbonate divided by the hydronium ion concentration here. That. Okay, so plugging in the values here, we're going to get 2S quantity squared times S divided by 1.0 times 10 to the minus 3 minus S first.
Uh-oh, we can't solve this.
Yeah, well, either you're going to have to
It's
use...
cubic.
Yeah, it's cubic, so you're going to have to do... if the simplifying assumption fails, you'll have to do successive approximations
Oh no!
to solve.
Using all of our tools.
We can see if the simplifying assumption works or not when we calculate KSPA. What is KSPA for this? 0.1802. This is not looking good for the simplifying assumption. And so it's looking like successive approximations to solve this, right?
Dang it.
Yeah. Unfortunately. Or maybe, I don't know. Did it? All right. Versus this. So simplifying assumption likely is going to fail, and we'll use successive approximations. So we're back to that. Versus if this were the final, you know, let's say this were buffered. If those were buffered, no matter if we consume some hydronium or add hydronium, the hydronium concentration is going to stay stable because the buffer is going to do that. And so if we have this, then what does this problem turn into? Well, this is going to be, if that were the final concentration, then this is going to be 2S quantity squared times S divided by 1.0 times 10 to the minus 3, which is
A bit easier.
Yeah, a lot easier, right? And so it's very important that you determine this because it makes the problem, yeah, easier or harder. Sometimes I tell them that's initial concentration, but they overlook it because we make it the final concentration. So it just makes the math so much easier. All right, there are other things that are obviously pH dependent. Like, for example, magnesium hydroxide.
Magnesium hydroxide?
Yeah, magnesium hydroxide goes magnesium plus 2 hydroxide.
Oh yeah, I had a whole bunch of ammonia and MgOH precipitation. Remember?
Yeah. Yeah. And so this one, I mean, you could do two ways for this one. I mean, one way is you could go from pH to POH to hydroxide ion concentration, and then it would be like a common ion type problem, right? Common ion problem. The other way you could do this is like this. Versus a KSP8 type problem. For KSP8 problems, we take the KSP equation and then see what gets attacked by acid. Right? And so what we'll say is acid will attack what in this?
Hydroxide.
Hydroxide. Right? And that's going to yield 2 waters. But what is the K for this?
That's the water.
1 over kW.
1 over
Oh, 1
kW.
over is backwards, yeah.
1 over
It's
kW.
gonna be really big.
But that only takes 1 hydroxide out. And so we have another hydroxide, so we're going to attack that too. So we've got 2 hydroxides.
KW squared.
Right. And so this is going to be 1 over kW. And so when we combine this, the K for the net equation is going to be KSP divided by kW squared. And the net equation is going to look like this. Magnesium hydroxide, solid, plus 2 hydroniums is going to give us magnesium 2 plus 4 waters. Okay. And then we can just do a single ice table for this, right? Figuring out how pH is going to impact this.
Whoa.
Yeah, I don't know what that is. Okay, which brings us to sulfides. Sulfides are very let's look at something like copper 2 sulfide. Copper 2 sulfide, this is going to go to copper 2 plus sulfide, right?
Mm-hmm.
But there's a problem.
What is it?
There's a problem with of this KSP equation. And the problem with the KSP equation is this. What do you know about sulfide? It's a strong base. And strong bases hydrolyze water 100%. And so sulfide's too strong of a base to exist in water. Too strong to exist in water. And so this is not the KSP equation. Because what's going to happen is this. The sulfide, you're not going to have sulfide. The sulfide will attack water immediately. And when sulfide attacks water, what does it form? It forms No, we do it always, we do one proton at a time.
HS minus.
HS minus and OH minus. That's what's gonna happen. And so what we do is we combine these two things and we end up with this. Copper sulfide solid plus H2O liquid gives us copper 2 plus HS minus plus OH minus. This we call KSP dagger. KSP double daggers for sulfides. And the sulfides are always plus water because the water is going to be attacked immediately when the sulfide is freed from the lattice. And so if I want to calculate the solubility of copper sulfide, then let's do that. It's going to be a little bit more complicated than a normal KSP. And so what is the solubility of copper? So the example is solubility of the copper 2 sulfide equals blank, question mark. And so over here, I just set up my ice table. This is solid, so we can ignore it. This is liquid, we can ignore it. So let's just start from here. And so we assume nothing's dissolved. And then this is going to be plus what? S, right. Plus S, plus S, plus S. So S molar, S molar, S molar. And so the KSP dagger is just equal to S cubed, which means S is equal to the cube root. But that's just for this one. You know, there are other, just for this particular problem, because in other ones we have different ratios, right? So for example, if we're looking at silver sulfide, it would be totally different because silver sulfide would be Ag2S, which splits up differently. Or if we're looking at iron 3 sulfide,
why all of them are 0 molar at first?
because we assume nothing's dissolved at first. We reset it, so because we don't even know what they are, what the initial is. Obviously, it's already dissolved, you know, if it's equilibrated, but we just always do it that way. Make our life easier in the calculation. The more zeros we have at the start, the easier the calculation becomes. This is the whole, one of the reasons for resetting. But,
So you just reset it.
yeah. Right, let's do one more then. Iron 2 plus 3 sulfides. Is this right? No, this is not right, right? This is not right. But in this case, we end up with 3 sulfides, not 1 sulfide. And so we have to add how many waters to react with those? 3. And so this is actually wrong. The other way we could do that is we could just manually add the waters here. You know, if we wanted to, we could just say sulfide plus water here, sulfide plus water, and then, you know, combine all those. Or we could just go ahead and just look at it. Fe2S3 solid plus 3 waters for 3 sulfides is going to give me a 2Fe 3 plus 3 HS minus plus 3 hydroxides, right? Does everybody see where I got that? Just skip some stuff. So this would be KSP double dagger. KSP double dagger is in your book. You'd get the number off the chart and you can figure it out. And so if we're doing a solubility calculation, we would just do it like this. You know, we assume nothing has dissolved, right? And
Why do you make the assumption? How do you know the assumption's valid?
What would you put here as an alternative? Let's see. What's for your initial?
For my initial?
Yeah.
We have no initials. We don't know the initials.
And so what should you do? Should you give up on this particular problem because we don't know the initial, or should you just reset it and try to solve it?
Reset.
Reset. And so if we reset it, no matter what the initials here were, you know, and all the iron, there's no common ion. Common ion, I could be dumping in hydroxide in there, and I could start off with a huge amount of hydroxide, but all these ions are coming from Fe2S3, and so they're all going to split up stoichiometrically like this, so we just reset everything to the left, and then start. This is going to be plus,
2S,
plus
3S, 3S.
3s.
It's a lot of S's.
A lot of s's, so
18S cubed.
this is going to be iron 3 plus squared, HS minus, cubed, OH minus, cubed. Right? And so this is going to be 2s squared, 3s cubed, 3s cubed.
7 power.
And so this is 4, 27,
Wait, no, 8.
27. This is 3 to the, what is that? Yeah, that's going to be pretty,
Messy.
yeah,
Math.
right. If I made this into a common ion problem, let's say I threw in some hydroxide in there to ask you what is the solubility in the presence of 6 molar sodium hydroxide? Well, calculating the solubility here, that's not that bad. I mean, 'cause it's not that bad. And so let's make this into a common ion problem, right? What is the solubility? Should we add iron, HS minus, or hydroxide? What would you want to add for common ion? Hydroxide. This is solubility in 3.0 molar sodium hydroxide. We got sodium hydroxide. What do you think is going to happen? Will the solubility be higher or lower in sodium hydroxide?
Lower.
It's going to be lower. It's common ion, so it's going to be lower.
It suppresses the solubility.
Right, it suppresses solubility. So, but the thing is this the initial or is this the final? I'd like to say final because, you know, that's going to make it a lot easier. But initial or final? Yeah, definitely final is going to make it much, much easier, right? But if this were initial, then
it's going to go through a chain.
then I know that this is going to be 0, this is going to be 0 because I'm going to assume nothing, but this is going to be 3.0 molar. So now I'm going to have 3.0 plus 3s, which I'm going to have to plug in here, and I'm going to hope that the simplifying assumption works. But you know what? The simplifying assumption works. It'll work in this because KSP double dagger is very small. Sulfides aren't very soluble, right? And so the simplifying assumption works, therefore this problem is not that hard.
Can you just tell us if it's initial or final or?
Yeah,
Okay.
I'll tell you. If you didn't, I'll tell you, if you didn't use the simplifying assumption, then you're looking at a horrendous problem, right? So oftentimes people ask me, why do I have to use that? Or what's the purpose of learning that? Well, anyway, that's one way. What we know is the hydroxide concentration goes down, then solubility should go up, right? And so this is going to be influenced by pH, but you know, can I make the hydroxide go down to 0? Well, I just did it here,
don't
right?
put hydroxide.
Or can I make the hydroxide go negative?
No!
So what I'm saying is, okay, I can make the sodium hydroxide go down to 0, and that's going to maximize the solubility because I'll just have 0, 0, 0, but can I even make it more soluble? That is, add acid. If I add acid to this, then would that make it even more soluble?
Yes.
Yes.
because the acid is gonna attack the hydroxide.
Right, and so I say, you know, initially I said, well, this KSP is very small, so the simplifying assumption works. But if this were an acid solution, that KSP, this brings us to KSPA double dagger. KSPA double dagger is a little bit more complex than KSPA double dagger. The reason is because of this. There are two bases in here. Not only would acid attack hydroxide, but there's another base in here. What's the other base?
Sulfur.
HS minus. The Kb for HS minus, H2S is a weak acid, therefore HS minus is a decent base. And so we have two bases here that can impact. Yeah, and so actually we're out of time right now, so we'll talk about it next time. We'll do KSPA double dagger next time.
It's pretty interesting. What's the best recipe? Just tell me what. Just see how well it's done to you.
Which one of these K's and the KF, KS, KSP, 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 double dagger? Oh, Professor, in the book, I couldn't find where they have those double dagger numbers.
It's a little, there's a little
Is it in chapter
note.
18 or not?
It's a number 2.
I must have missed it. I took my glasses off, so it's gonna make it even worse right now. But
Oh, go to either chapter 18 or appendix D.
I'm in D, and I got kilojoules, so I have KAs.
Do you see this B?
Oh yeah, that
Rather than calling it-
the sulfide one.
Rather than calling it B, I'm calling it double dagger.
Okay, yeah. So iron sulfide that we just did was a double dagger.
Right, and so all the ones that are marked B are double daggers.
Good to know. Thank you. I was looking for that little symbol. I couldn't find it.
Oh,
I was going crazy.
Yeah, sorry. There's another chart with double dagger. But it's not there.
That's fine. As long as I know what it is, I'm good. But you're like, yeah, they're in the book, and I looked, I couldn't find it.
Yeah, it's just to differentiate it from the regular KSP, that's all.
So for that HCl problem.